Math 1314, Tyler Junior College, Section 5.1, 2x2 Systems of Linear Equations, Applications, Rate. I like these kind of word problems too. A lot of people groan at them because this just sounds like a standard typical word problem. If a train goes this far and this fast and another train goes that direction that fast, it's something like that. But goofy made-up word problems aside, like the ones you typically see in stupid Facebook memes, rate problems are fairly straightforward if you just know a couple of basic things. Let's read this one and then I'll tell you what those basic things are. Rowing with the current in a river, a crew travels 16 miles in 2 hours. So here's a picture of the current of the river going to the right and the canoe, or whatever the boat is, also going towards the right, so they're paddling that way. Rowing against the current, the same crew travels 8 miles in 2 hours. So on the return trip, with the river still going to the right and they're going to the left, they travel less distance in the same time. Assuming the river's current is constant, find the current's rate and the rate the crew travels in still water. So what are the two things we need to know to attack this? Well, first let's identify the variables, which are clearly defined by the question. Find the current's rate and the rate the crew travels in still water. We'll let x be the current's rate, how fast the current is moving, and we'll let y be the crew's rate in still water. If the water were just sitting and not moving at all, not working with them or against them. So what are the two things we need to know? Well, number one is the relationship between three values that we're looking at here. Distance, rate, and time. And the equation that ties them all together is rate times time is equal to distance. This is something you already know intuitively, and I'll prove it. If you drive 60 miles per hour for 2 hours, how far have you traveled? Well, 60 miles per hour times 2 hours is 120 miles. 60 miles per hour times 2 hours equals 120 miles. But how can we use that to help solve this? And where's the system of equations? I'm going to set up a table with 3 columns, one for rate, one for time, one for distance. But we're going to have 2 rows. One to represent when they're going with the current, and one to represent when they're going against the current. So let's analyze what we're given. With the current, a crew travels 16 miles in 2 hours. 16 miles is a distance, 2 hours is a time. Against the current, the same crew travels 8 miles, that's a distance, in 2 hours. The only thing missing from both of these are the rates. But our variables kind of represent rates. But what do we put to represent going with the current and against the current? The first thing you need to know is the equation rate times time equals distance. The other thing you need to know is how these currents work when they're working with each other and against each other. We're calling the current's rate x, so I'm going to put an x under these blue arrows pointing to the right. And we're calling the crew's rate y, so I'm going to put a y above the green arrow, the one on top pointing to the right, the one on the bottom pointing to the left. But how do these rates work relative to each other? In a word, physics, and another word, vectors, but more simply put, plus or minus. When the rates are working in the same direction, the collective rate is their sum. So for example, if the river were traveling 5 miles per hour and we were paddling at 2 miles per hour, then the collective work, or the collective rate is 5 plus 2 equals 7 miles per hour. By contrast, if you're going against the current, then the rates work against each other and the collective rate is the difference. how fast the river is going minus how fast you're paddling against it. So if the river were traveling 5 miles per hour and you were paddling 2 miles per hour, then your rate would not only be the difference, 3 miles per hour, but you would be going backwards because you're not paddling fast enough to compensate for the speed of the river. With the current, the collected rate is the sum, so x plus y. But against the current, the rate is the difference. Now here's where we have to be careful. Be a little bit nitpicky here. I may need to change a little something. What's going faster, the river or the boat? It has to be the boat. Because think about the going against the current. If we were paddling slower than the river is going, we wouldn't be going forwards, we would be going backwards. We did go forwards, we went forwards 8 miles. So really, the blue arrow should be shorter. I'm really thinking about this from a physics perspective. And the y arrow should be longer, because if we were paddling slower than the river, we would not be able to go 8 miles forwards. When we were paddling against the current, we would go 8 miles backwards. For a positive rate, we have to do our speed minus the river speed. So we'll say y minus x. The addition problem doesn't matter. Addition is commutative. The subtraction problem, it matters. So our speed minus the speed of the river, speed of the current, which is taking away from our overall speed. So if we can get past that part, then we can set up 2 equations by using the equation rate times time equals distance. So x plus y times 2 is equal to 16. Y minus x times 2 is equal to 8. It's a system of equations now. Let's distribute. 2x plus 2y equals 16. Second one's equal to 8, and I'm going to distribute the 2, but to line up like terms, I'm going to put the negative 2x first, and then the positive 2y second. Well, this is an easy system to solve. It's ready for an addition. The x's are already an opposite pair. X's cancel. We get 4y. 16 plus 8 is equal to 24. Divide both sides by 4, we get y equals 6. Our crew is paddling at 6 miles per hour. Which rate is what's the rate of the river? Well, pick your equation. Let's pick the first equation. 2x plus 2y equals 16. 2x plus 2 times 6 is equal to 16. Remember, y is equal to 6. This is 12. Subtract 12 from both sides to get 2y is equal to 4. Divide by 4 to get 2. And I'm sorry, this should say x equals. Our river is going 2 miles per hour. Our crew in the boat's going 6 miles per hour. Let's see if this makes sense. Together, they're going 8 miles per hour when they're going with the current. 8 miles per hour for 2 hours is 16 miles. On the return trip, the river is working against them, so the total speed they're traveling is 6 minus 2, which is 4 miles per hour. 4 miles per hour times 2 hours is 8 miles. I'm kind of curious what would have happened had we left this as x minus y. If you kind of get this and don't want to follow up what would happen if we had the subtraction problem backwards, you can shut off the video now. But the theoretical mathematician in me is not letting it go. So feel free to end the video now if you like, but I am going to chase that rabbit down that hole. What would happen if we had the subtraction problem backwards? If the subtraction problem were backwards, and we wrote x minus y, we would have gotten 2x plus 2y is equal to 16, 2x minus 2y is equal to 8, add to get 4x is equal to 64, 24, get x equals 6, and we would have gotten y equals 2. That was the same answer we got before, wasn't it? Yes, but notice we got them backwards, that the river is going 6 miles per hour and the crew is going 2 miles per hour. And this sets up the scenario where they don't go forward when they're going against the river. They would actually combined, they would still be going 4 miles per hour collectively when they're going against the current, because 4 is the difference, but because the river's going faster, it would be going 4 miles per hour backwards. So they would be facing this way and paddling frantically, all the while moving backwards. I knew there had to be a consequence if we switched the subtraction problem. Basically, we would not have captured the correct scenario about them going 8 miles in 2 hours. Although honestly, it doesn't say they went 8 miles per hour forward, but you know, we just kind of assume that.